Before we do this, we just look at the Coriolis force on Earth. So the Coriolis force on Earth is very, very similar to just the turntable example. But it has a little bit in addition. Here you can see the equations again here. These are the equations. And you can see that on one, in the equation for U, there you have a V here on the right hand side, and in the equation for V you have a U, and a plus and a minus. And if you analyze this, it's the same feature. You have a force which is x 90 degrees with respect to the flow direction. Okay, but now there is an F there, and the F is the so-called Coriolis parameter, and it's actually given by 2 times the omega. Okay, and omega is 2 pi over the time of one rotation, and on Earth it would be just the seconds of one day. So how many seconds? But then there is something that modulates F. This is the geographical latitude, the sign of the geographical latitude. Okay? And again, if you look at it, look at the details, what you learn is, firstly, the Coriolis parameter is 0 at the. Why is it 0 at the equator? Is because if you place a plane onto the equator and you let the Earth rotate, the plane goes around, but it never rotates around its own axis. The other thing that you learn is that there's a sign change between the northern and the southern hemisphere. It's like the sine function. Changes sign from if you cross the equator. And this, you can also visualize that. You look at Earth and look at the rotation of Earth. Okay, you can see that it rotates one way if you place the North Pole at the top. But if you turn it upside down, actually with the South Pole on top, the Earth rotates in the opposite way. So if you place your planes onto the poles, you can see that the planes rotate like a turntable does. Okay, but the sense of rotation changes between the northern and. So now what we call an F-plane is if we put a plane centered on a specific latitude, and then we can simulate the Coriolis effect in a Cartesian coordinate system. So we don't really need to, on relatively small scales of say up to 10 degrees or 1,000 kilometers, we can use still Cartesian coordinates. We don't need to use spherical coordinates, which would make it more complex. All right, so now the next thing is, okay, let's try and just try it ourselves. How do we simulate the Coriolis? And just plug in using an explicit approach for the for the terms on the right hand side. Okay? And this is shown here, explicit approach. And it shows you now the simulation using using the finite difference. You see the simulation? And what you actually see from the simulation is you don't get a closed path. You get sort of a spiral path. We have a look at that on the next slide of why it doesn't work. But this is just to give you a reminder of how do you formulate these equations and the differences. And this is shown here, this equation. For you can just use a simple forward difference. Okay, forward difference with the time step, you get un plus 1 is the value of u, is the value u at the time level n, plus you have the correction that comes from the Coriolis force. Delta t is the time step, and okay, f times vn, and so on. This is the most basic way. And then you plug it into an iteration loop. Okay, you plug in an iteration loop, and then what I've done here in this to illustrate the location is you indeed use a little particle, and you have a displacement predictions. Yeah, have a look at how we've done it with Lagrangian particles. This is how you illustrate the trajectory of. So why is it that it doesn't work? What's the problem? Okay, and the problem is illustrated on the next slide. Okay, so now, because you have a finite time step, so this is what's shown here on this. You have a circle. So you want to have a solution actually which moves a particle along a circle. Okay? So you actually have a velocity times a time step. So this is where you start. And you could imagine that you now move first your particle along that velocity, so along the red arrow, and then you use the Coriolis force, which operates at a right angle here to the left, to move it back. Okay, so now if you do that at a right angle, you will always end up outside the circle just because the time step is finite. Okay? What you actually needed in order to move your particle with the Coriolis force back onto the circle is you actually need a slightly different angle. Okay? So that's the problem. So the explicit approach does not work for the Coriolis force. Okay, it can also be shown that the speed of the parcel actually increases gradually. Therefore, the explicit implementation of the Coriolis force is always numerically unstable. You get the speed that increases, so it gets faster, and you get onto these spiraling paths. This doesn't work. So you learn another trick. So how do you actually implement the Coriolis force? That's it. The second trick you already learned about the semi-implicit approach for bottom friction, which was one little trick. Coriolis force is another problem.